Good evening and welcome to Tracking the Tropics. I'm meteorologist Wes Hohenstein in Raleigh, North Carolina. Tonight, we're 3 months and 8 days into the hurricane season, and once again, we have our hands full. 3 systems in the Atlantic we're keeping an eye on, and maybe a 4th. I'll break down each one for you in 60 seconds, and we'll show you how satellites play such an important role in hurricane forecasting. Plus this on week 15 of Tracking the Tropics.
I'm John Conway, Jackson, Mississippi. The 2020 Atlantic hurricane season has already broken records and it continues to be active. Tonight, we're going to talk about not just the goings-on in the tropics, but also how global climate change could affect future tropical seasons.
All right, John, we've also got some history today. The worst hurricane ever to impact the United States made landfall on this day 120 years ago. I'm going to look back on the Galveston hurricane, but tonight we're looking out some 450 miles off the North and South Carolina coast is what the National Hurricane Center is calling its next potential tropical depression. It has a 30% chance of developing into a tropical system in the next 2 days and a 40% chance in the next 5 days. So a couple things to point out here. Number one, those of you on the East Coast have probably already felt some of the impacts of where this system might come from. After a nearly perfect holiday weekend with sunshine, no rain, and low humidity, all the moisture that's out there in the tropical Atlantic off the East Coast has turned around and come back toward the East Coast. So we have clouds, we have rain, and we have higher humidity. And it's that type of atmosphere that is also encouraging a little area of disorganized low pressure and some thunderstorms to possibly develop into a tropical depression. So 2 very important things to point out here. First of all, 30 and 40% chances of anything happening, it's not really that great. It's not even 50-50. So we're not really overly impressed that something could develop. The second thing I always like to do with the system, push aside the numbers. Let's use the tools we have. Let's just look at the system. So if this thing did have a center, it would be right about there. But if you look right about there, there's not a whole lot out there to be impressed by. So those 2 facts, the eye test and the numbers we're looking at here, don't have me overall worried or encouraged that anything is going to develop. If it were to happen, it would not be that significant. But aside from all of that, no matter what happens, all of that moisture out there, the cloud cover, the rain chances, the higher humidity, that is going to continue to move inland and bring more of the same across the East Coast the next couple of days. Not significant rain, severe weather and flooding, but a few scattered showers. Now, more importantly, if something were to develop, we continue on our record pace in this 2020 hurricane season. Let's look at what the computer models are saying, because either way, some of that moisture is going to drift inland like it has already started to do. Again, if there were a center, it's about 450 miles off the coast of North Carolina. So here are the latest computer model runs. We don't have the full evening suite in yet. So these are mainly the Tuesday afternoon model runs. And as you can see, they're all in pretty good agreement that if something were to form, and even if it doesn't form, it is going to drift more toward the North Carolina and South Carolina coast. Now remember, you don't look at these lines and assume this is going to be a major tropical system or even a tropical system whatsoever. This is just where a center of circulation may forecast to go. So that's all we need to take away from the computer models. What we do have is another system, 2 of them, even farther away. This one more than 2,000 miles away. It is Tropical Storm Paulette. Earlier this week, it became the earliest forming P-name storm on record. It's got 65-mile-per-hour winds, and it's moving kind of slowly northwest at 8 miles per hour. And again, if you do the eye test with this, the center of circulation is really lopsided, because if you look to the north, that's where all the thunderstorm activity is. But when you look to the south, there's nothing but blue sky and blue ocean. That's a very lopsided system. Still, with 65-mile-per-hour winds, it's just about 10 miles per hour away from becoming a hurricane. Now, the official forecast track for Paulette doesn't actually have it strengthening to a hurricane. However, it remains a tropical storm as it kind of weaves its way northwest and eventually turns more north over the course of the next several days. The point here is this doesn't look like it's going to impact the United States, but we're only halfway through covering everything going on in the tropics. I've got two more things to tell you about. The other one is Tropical Storm Rene, which earlier this week became the earliest forming R-named storm on record, the 17th named storm. This one does not look that impressive, moving along west at 16 miles per hour, really just coming off the coast of Africa, so it hasn't had a whole lot of time to get its act together. It's got 40-mile-per-hour winds, and more importantly, the forecast track for Rene has it curving pretty significantly to the north, and this has been a trend that we've been seeing over the last couple of days, so we're not too worried about that. That should avoid the United States well before it comes anywhere close to land, but it could become a Category 1 hurricane later this week. And the fourth thing we're keeping an eye on as we look at the big picture across the Atlantic, again, that potential area of low pressure about 500 miles off the coast of the Carolinas, 1. There's Paulette and Rene, 2 and 3. But do you see this area of thunderstorms, this cloud base coming off the coast of Africa, still over the continent now? That is a pretty significant complex of thunderstorms that already the National Hurricane Center is giving an 80% chance of development in the next 5 days. That's a pretty amazing statistics. The thing is still over land. Yes, it's an impressive area of thunderstorms, but already an 80% chance of developing. Now, what I find interesting about everything going on this hurricane season is we have something to contrast it. Did you see what happened earlier today in Colorado? Wyoming was in on it too. After record high temperatures in the 90s last week, they didn't get out of the 30s today. This from Colorado, and they have snow. So while parts of the United States are dealing with maybe some tropical moisture, another part of the United States is dealing with its first taste of winter. But we continue on in this tropical season. I mentioned Paulette and Rene. There are now just 4 names left on the 2020 Atlantic hurricane season name list. Of course, we've made it through Laura. We started with Arthur even before the season officially began. Sally, Teddy, Vicky, and Wilfred are the next named storms on the list, and if we go past that, we will go into the Greek alphabet. Now I want to put in little lines under every name that was the earliest forming storm on record. Starting back with Cristobal, Eduard, Faye, Gonzalo, look at all the storms have been earliest forming on record. This is a great indication that we could be heading for record territory. And when we look into September, so we're 8 days into the new month, this is where storms generally form in September. This is a great graphic I love to show when we start a new month from Dr. Phil Klausbach, Colorado State University. He was on Tracking the Tropics with us earlier this season. He has plotted every storm that has formed since 1851. So we've got a lot of data out here, and just look at all the activity. What I find interesting is we get storms that form in the Gulf of Mexico. Everywhere you see a dot is where a storm formed. Off the East Coast, in the Caribbean, a lot out in the far tropical Atlantic. But compare that to where we've come just in the past 2 months. This is the same map for July. So these are all the storms that have formed in July since 1851. Tropical storms and hurricanes. Not a lot of dots out there. Obviously, even though things are hot on land in July, they really don't start to heat up in the tropical Atlantic. Again, there's September, and look at July. So an amazing ramp up of activity just in the past 2 months. And it all makes sense because September, on average, is our busiest month in the Atlantic. 34% of all tropical activity happens in the month that we are living in right now. So let's break down big picture and long-term what's going on. I want to welcome in our first guest. Joining us now from Jackson, Mississippi is meteorologist John Conway from our sister station down there. John, good evening to you. I'll start you off with just getting your thoughts on what an incredibly busy season. I've got to scratch my head and do a lot of other things every time we get a new named storm. Can you believe what we're living through right now?
Well, I can believe it because I lived through the 2015 or the 2005 hurricane season, which was another record breaker where we just saw an incredible pace of tropical storm formation all throughout the year. I'm going to bring up the list of storms that we've had for this 2020 hurricane season before. Wes was talking about that just a moment ago. These are all right now. We have Paulette and Rene, active tropical storms. Now, I hear this season compared a lot to 2005. There are a couple of big differences that we see so far. Right now, with the exception of Hurricane Laura, a very, very powerful Category 4 hurricane when it made landfall in Louisiana. So far, we've had relatively weak storms, a lot of tropical storms. We didn't have our first hurricane until Hannah at Category 1, then Isaias, Category 1. But just because storms are just tropical storms are relatively weak Category 1 hurricanes doesn't mean they can't cause trouble. Isaias caused all kinds of problems up in the Northeast, in my former hometown, up in Connecticut. That's a big difference between 2005. 2005, this time we already had several powerful storms like Katrina. And the other thing I want to kind of mention here is that for us as meteorologists, we kind of make a big deal at the pace, about the pace at which we've been naming storms so far this year. We're talking about the record first C storm, the record first F storm, the record first P storm. And that's kind of an implication for the climatology. Is that a sign that things may be changing in our climate or whatnot? But even in relatively quiet seasons, I think back to 1992, probably one of the quietest seasons of my lifetime, we didn't have our first named storm until about the mid-end of August. And that storm was Hurricane Andrew, one of the most devastating storms to strike the United States. So active season, a lot of names, things coming very, very quickly. So far, though, with the exception of Laura, we haven't had very many powerful storms, just that one major storm. But nevertheless, these storms could still be dangerous.
Yeah, great point, John. You know, a lot of volume, but not a lot of impact, thankfully, with the exception of Laura. Let's talk about the trend we've seen over the past few years. Walk us through some of the things that are contributing to this long-term trend of lots of tropical activity in the summer.
Well, first, let's take a look at why a lot of this happens here. We're going to take a look at global circulation, going to kind of give you a little crash course here in atmospheric dynamics here. What happens in the Earth, is that up in the poles, we have a deficit of heat. We don't get a lot of heat up there. It's cold at the poles. We know that, and that's because they either get, very, very shallow sun angles, or in fact, for parts of the year, they don't see sun at all for several days in a row. Down here in the tropics, though, they get a lot of direct sun, and they get a lot of heat, and you have what we call a temperature gradient. A gradient just means a change in a value over a distance. So as you travel from the poles down toward the equator, the average temperature rises. We call that a gradient. And Mother Nature abhors a vacuum, and she doesn't like gradients. So what the atmosphere and the oceans are constantly trying to do is redistribute all of this heat down here and spread it out to the north. It does that through atmospheric wind and circulation. It also does it through oceanic circulation here. We get these big ocean currents that take this warm, energy-rich moisture down here by the tropics. In fact, this is Tropical Storm Paulette right there. Moves it up, takes a more hot, warm air from the Caribbean, from the Gulf of Mexico, moves it up to the Gulf Stream, keeps the east coast of the U.S. on the warmer side, and then it mixes with cold air coming down from the poles, the Arctic Circle, and then that cold air comes down, and the cycle begins again. So the oceans are constantly trying to balance and bring this imbalance of warm and cold temperatures, bringing them equal together. It's a constant struggle. Sometimes you get too much warm air down in the tropical regions, and that's when you can get hurricane formation developing down here. Hurricanes are big heat engines, and they're a very quick way to move heat energy out of the water because they feed on that heat energy from the water and move it quickly up into the atmosphere. And because the atmosphere is a gas, it's much less dense. It can move that warm energy up to the higher latitudes much, much more quickly. Now, where climate comes into play is when we start warming or cooling these temperatures down. We're going to take a look at water vapor capacity. Wes may have said there's going to be no math in this presentation. Well, he didn't realize that he was bringing me on the show today. This is one of the most important equations in meteorology, the Clausius-Clapeyron equation. Now, I'm not going to go through what everything in this equation means, but all I'm going to say is that it relates how much water vapor the air can hold in very crude terms. Air, of course, doesn't hold water vapor, but it relates how much water vapor it can hold to its temperature. And here we have the graph of this equation along typical temperatures on the Earth. Actually, these are in degrees Celsius. I didn't notate there. This is degrees Celsius, -30, all the way up to 50 degrees Celsius. And these are all temperatures we can see on the Earth's surface. Now, something to notice here, this is an exponential equation, and here's what that means. Look at how the change in the maximum water vapor, this is saturation vapor pressure here in units of kilopascals, all that means is just how much water vapor is in the air. And remember that water vapor is the fuel for severe thunderstorms. It's also the fuel for tropical storms. As you look here from like 10 degrees below 0 Celsius to 0 degrees Celsius. 0 degrees Celsius is 32 degrees Fahrenheit. The maximum amount of water vapor the air can hold, again in crude terms, is maybe 1/2 of a unit, 1/2 of a kilopascal. But then as you go from 0 to 10, this is 32 Fahrenheit to 50 Fahrenheit, it goes from maybe just below 1 to just below 2, so it increases by maybe 1. That increases by maybe 1.5, then 2, then 4, then 6. So for every degree the atmosphere gets warmer, for every degree that the water gets warmer, there is an ever-increasing amount of fuel in the atmosphere that these storms have to feed on. That is more energy that our global circulation is trying to spread throughout the planet to get rid of that temperature gradient that we were talking about before. So this is kind of a scientific look at why an increase in temperature overall in the tropics can mean more numerous and potentially more severe storms, keeping in mind that even in a season that isn't very busy, like 1992, you can still have devastating storms. They're very delicate structures. You have to have the right ingredients in place, and you have to put them together under the right conditions as well.
John, great point about how important the science and math is. I often compare it to earthquakes and the Richter scale, how a 5 up to a 6 isn't just a jump in one. It's exponentially worse.
Yes.
When you're talking about shaking the earth and, you know, exponentially increasing how much moisture we have. That's what these storms fuel off. I think we take for granted, though, that these things just spin up like that, like it's no big deal. But forming a hurricane is really a big deal out in the ocean.
It is, and this is the case. When I talk to school children a lot, you know, I tell them, like, we talk about tornadoes a lot. You know, we're very tornadically active down here in the Deep South. Tornadoes are actually very, very delicate structures. You have to have just the right set of conditions for a tornado to form. It's the same thing with a hurricane as well. You have to have the right conditions. I often equate it to like baking a cake. You can have all the ingredients for the cake. You can have your flour, your water, your eggs, your sugar, whatever else you put in to bake a cake, and you put those ingredients on your counter. Well, you don't have a cake. You have to combine those ingredients in the right proportions under the right temperature conditions before you can get a cake. And that's exactly what happens with the formation of thunderstorms. For example, one of the things you have to have for tropical storms to develop is warm water, because unlike storms that form over land that feed on water vapor from the air, hurricanes and tropical storms, they feed on water vapor that comes from water. And there's a lot more water vapor. That's why hurricanes are so much larger than a severe thunderstorm. That's part of the reason why they produce so much more energy. So one of the things is sea surface temperature. How warm is the water? And typically we want to see waters that are 26 degrees Celsius or warmer. And 26 degrees Celsius, I'm guessing, is probably about 80 degrees Fahrenheit. I know 86 Fahrenheit is 30 Celsius. Looking right now, these are the current sea surface temperatures in the Gulf of Mexico and off the East Coast. These temperatures well above 26 Celsius. They are well above 80 degrees. We're seeing some 88s off the west coast of Florida, 85s and 86s out in the Gulf of Mexico. Even as we look out toward get out into the Atlantic here as I slowly scroll this out here. Look at this. As we look into the Caribbean, the Leeward and the Windward Islands, we're seeing temperatures in the mid-80s, you know, around Puerto Rico down into the Caribbean. So you have to have those sea surface temperatures in place. So that's one ingredient you have to have. The other thing you have to have is moisture in the atmosphere. This is our water vapor satellite. This is telling us how much water vapor is in the air. Where you see darker coloration here, that's where the air is drier. Where you see lighter colorations here, that's where the air has more moisture for these storms to feed on. This, in fact, right here, Tropical Storm Paulette. Of course, a lot of water vapor around a tropical storm. Kind of moving in this direction, though, is moving into an area of some drier air, so that may not be conducive to the storm. But if we increase the amount of water vapor in here, and we can do that if we were to increase the average air temperature over here, increase the average water temperature by even just a degree, Paulette would have a lot more moisture to feed on as it gets up into that area. And then, of course, we talk about shear all the time. You have to have good shear conditions as well. Now, we're going to talk a little bit about shear in just a few minutes, but again, tropical systems don't like shear, which is a big difference from thunderstorms that form over land. So these are all these ingredients you have to have. You have to have the moisture, you have to have the heat energy to fuel these storms, and they have to come together under just the right conditions where there's not a lot of wind blowing around, you're down by the equator, and you start to get some thunderstorms forming. You get a little bit of lift, then everything starts slowly spinning, and due to a principle called the conservation of angular momentum, that spin gets tighter, 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 and so long as you're continuing to fuel that storm, you're going to have an ever strengthening tropical system. And again, you interrupt any one of those factors, the storm will dissipate. So again, hurricanes as well, they're very powerful, at the same time, very delicate as well.
Delicate and finicky, too, is how I like to describe them.
Absolutely.
You know, we talked a lot about wind shear early in the season. There was too much wind shear. There was too much Saharan dust. We didn't have the right conditions, and we didn't see a lot of tropical activity for a short amount of time. But it's kind of the exact opposite with severe weather on land. Wind shear can be deadly sometimes.
It can, and in fact, I'm going to bring my whiteboard over here and kind of make this a little bit of a multimedia presentation here to kind of talk about why shear is good in some conditions and why it's not so good in others, because you hear meteorologists talk about shear all the time. When we're talking about severe thunderstorms over land, we're talking about how, you know, we're looking at good shear conditions, a lot of a highly sheared environment, which is good for powerful rotating thunderstorms. But when we talk about the tropics, we're talking about, oh, shear is a bad thing. You know, we're looking for portions of the tropics that have very, very poor shear. So if our director can kind of zoom in here on the board, I'm going to kind of try to demonstrate just exactly why that is. So when we're talking about severe thunderstorms, severe thunderstorms, these are storms that form over land. Down here in the deep south, we get them in the springtime. We get violent tornadoes. Then in the summertime, the violent tornado risk moves up into the upper Midwest and out into the Great Plains. When a thunderstorm forms, here's the land surface. And thunderstorms form, and they feed on the water vapor in the air. So you start to get a little bit of lifting going on. Three things you need for a severe thunderstorm. You need heat, you need moisture, and you need some form of lift. We're not going to get into that. That's a whole field of dynamics here. But you start to get a little bit of lifting going on, and then as air rises, it cools. And if it cools enough, you'll start to get clouds forming. And if it continues to cool enough, as it forms the clouds, heat is released. We call that latent heat of vaporization. And then eventually the air becomes warmer than the air around it, and then it just continues rising and forming a thunderstorm cloud, which often kind of, looks like this. Now, what is shear? And I probably should define that first. Shear is how change in wind speed or wind direction over height or over a distance. So for example, if here we have wind out of the west at 10 miles per hour, down here near the ground surface it's at 5 miles per hour. This is an example of shear. The air is blowing at different speeds at different heights, and what that can do, that can cause a rotation to form in the atmosphere. You can also have directional shear. Erase this, kind of hearkening back to my old days of teaching in college. If you have a point A and point B, and here the air is flowing out of the south at 20 miles per hour. Here it's flowing out of the west at 10 miles per hour. We have air in different speeds and different directions over a distance. So that's what shear is. Now, if the air here at point B, as I erase that, is also out of the south at 20 miles per hour, this is not a sheared environment because the air is blowing in the same direction and at the same speed. So that's a very important thing to remember. If the air is not moving, or if the air is moving at the same speed and the same direction, that is a low shear environment or a weakly sheared environment. If the air is moving at different speeds and different directions, we call that highly sheared. So I'm going to erase this and go back to our little diagram of the thunderstorm here. We have a thunderstorm building. We got the rising. The clouds are starting to form. But if we don't have any shear in the atmosphere, this storm is just going to develop straight up. And as it does so, it's going to start raining. It's going to rain down right on top of itself. And as it does so, the storm is going to snuff itself out, and you're not going to get a severe thunderstorm. But if we have shear in the atmosphere, and here I am, I know I'm getting long-winded here, but say up here, you know, the wind is blowing at, 50 miles per hour, and down here at the surface, blowing at maybe 10 miles per hour, maybe even in a different direction. As that storm begins to rise, it's also going to start tilting. So then you get your thunderstorms. See how a lot of times these big severe thunderstorms look like this? Now, the air is being sucked up, but the rain falling out of the severe thunderstorm is not snuffing the storm out, and the storm can continue to grow, and under the right conditions, you can even have a thunderstorm develop. Now, with tropical systems, it's totally different. I erase this here. With tropical storms, they're vertical. You know, here's the water, and you start getting evaporation out of the water. They're vertical systems. You know, area of low pressure here, area of high pressure here. Everything moves up, rains out. Cold air comes down, picks up more heat, water vapor, gets warm, rises up, it rains out, and it cycles on all sides of the storm. So if you were to put a bunch of shear in here, it's going to rip the tropical system apart. I know this is kind of this is a crash course in tropical dynamics here. But that's why shear is good for severe thunderstorms, but it is bad for tropical storms. Tropical storms need to form perfectly vertically. You see lots of symmetry in a tropical storm. They're very, a powerful tropical storm, usually very symmetric. Remember Hurricane Laura, if you were watching the coverage, just a beautiful, almost perfectly circular eye. If you had winds blowing at different directions at different heights in the atmosphere, it's going to blow that storm apart, and you're going to get a significantly weakened storm as well. So kind of a long-winded explanation there. I hope it kind of makes sense why shear is good. Now, of course, here on our tropical satellite, this is a forecast satellite here. We see very poor shear right here. This is about 30 degrees north latitude. But as we look off to the west here, where you see the red color, that's where you have a weakly sheared environment. Look at these conditions off the Carolina coast, Florida, into the Caribbean. See those reds and magentas? Those are areas where there is very little shear, and if we can get a tropical disturbance out here, we have one of the ingredients for another potentially powerful tropical storm.
John, that really is a great explanation, and I think what we all need to take away is shear is bad for hurricane development, but it's good for severe thunderstorms over land, and we want it sometimes and we don't want it the other. John, I want to wrap it up with you and get you out of here on this one. One of the things that you guys have to deal with a lot in Mississippi, and it has a little bit to do with what you just talked about, is, sometimes the hurricane itself isn't your biggest problem in Mississippi. It's what is produced as a side effect, tornadoes.
Exactly. In fact, this could be another huge, long explanation. I'm going to try to keep it very brief. But yeah, that was an issue. Hurricane Rita back in 2005 did not hit Mississippi. It hit southwest Louisiana, southeast Texas, not very far from where Laura made landfall. And if I recall correctly, we had 49 tornadoes in Mississippi. So really, the actual, the winds and the storm surge from Rita weren't the biggest headlines here in Mississippi. It was the tornadoes. I'm going to bring my good old trusty whiteboard back here. Again, I'm going to try to keep this as brief as I can to explain why. As I erase this here, one of the things that I teach when I go to talk to schools to talk to children about severe weather in Mississippi, you can't talk about severe weather here without talking about tornadoes. Now, of course, we do get our severe weather season in the spring. Now, what happens with a hurricane, as I move this back over here, here's your hurricane. Just represent a big circle. Here's the eye of the hurricane. We talk about the right front quadrant of the hurricane. So if the hurricane is moving this way, this is the direction of movement, we talk about this portion of the hurricane, the right front quadrant. This is where tornadoes are most likely to form. Now, tornadoes can form anywhere in the hurricane, but they're most likely here. We can change this around. If the storm is moving this way, like Hurricane Hannah did when it made landfall on South Texas, then this becomes the right front. You always look at it relative to the movement. Now, I'm not going to get into the details of exactly why there's pressure gradient forces, Coriolis forces in effect, but what does happen is, here's the water, and then land, and the hurricane is moving this way. We have very strong winds out here over the water. The water is pretty flat, so we could have, 80-mile-per-hour winds here, 80-mile-per-hour winds here, and right down here on the water surface, maybe 75, because there's a little bit of friction between the wind and the water. But when those winds get over land, you have trees, you have buildings, and you have hills. So there's a lot more friction. So up here, as that hurricane makes landfall, the winds up here are still blowing at 80 miles an hour. Here, though, maybe they slow to 75, and down here, they may slow to only maybe 30. So now, we were just talking about this, now we have a sheared environment here where the wind is blowing at different speeds and in different directions. Now, I'm going to change this to look from top down. So that's why the wind speed changes, because of the friction is so much higher over land. Now, as we look top down, here's the coastline, here's like the Gulf of Mexico, and here's land, here's Louisiana or Mississippi. What happens is, up high in the atmosphere, you have the winds blowing strongly this way, but down by the surface, where the winds are blowing slower, it's almost like they want to be sucked into the eye. That's pressure gradient force. Though these winds down here at the surface, they start to turn in toward the center of the storm. Now we have rotations going on here. And when you have those rotations, some of them could become tight enough and some of them could reach the ground. And that's why you get a lot of tornadoes in that right front quadrant of the storm, which we were very nervous about during Hurricane Laura, because Laura was another big storm in pretty much the same spot, and Mississippi was on the northeast quadrant of that storm, that right front quadrant. Fortunately, we didn't have as many tornadoes as we did with Rita. Rita, I believe, was 49 for the whole state. I think in Laura we had maybe 1 or 2 warnings, and none of them were on my shift. So it was, we really lucked out with Laura there. So that's why a very, very brief introduction to why the tornadoes tend to want to form in that right front quadrant of the hurricane, but they can form in any quadrants. This is just where it's more likely to happen.
Yeah, it's a big concern for a lot of us, John. Excellent science lesson, excellent use of the whiteboard. That is John Conway down at WJTV in Jackson, Mississippi. John, we'll see you down the road. Have a great night. Thanks for being with us tonight.
All right, thank you so much. It's been here. I hope everyone learned something.
Yeah, definitely. Learned and was reminded of a few things. All right, John down in Jackson, Mississippi. One of the most important tools that we use during the hurricane season is the satellites that orbit our planet, looking down at the storms as they form over the ocean. But how is it that we can get so much information from something that's so far away? Laura Smith spoke with NOAA on the many ways satellites play an important role in hurricane forecasting.
I'm Laura Smith, and we are speaking with Jason Dunyan. He is with NOAA. We are going to talk about satellites and their significance with the Hurricane Center and how they are being used to forecast the hurricane season. Jason, it is a busy one. Thank you so much for joining us here for this interview.
Thanks for having me.
Busy one out there right now. First, I want to start with your reaction when you look in the Atlantic right now.
Yeah, it's my reaction is that this has been a really busy season so far.
Talk about the satellites. Explain to people what satellites are being used right now.
So Noah, it's a pretty exciting time. You think back to the first weather satellite ever launched. It was April Fool's Day, 1960. And we've really come a long way. We've got a couple of different types of satellites. We've got polar orbiters. We call them JPSS is one of our more recent versions of the polar orbiters. And it's packed with sensors, looking at visible light, looking at infrared, even looking at microwaves. So the satellite's actually able to peer through the hurricane top to see the structure of the storm. And they're orbiting at about 500 miles up. You can actually see them at sunset when the sunlight's kind of bouncing off of them. So those satellites, all that information is getting sent to the forecast centers. It's getting sent to the modeling centers. So the data is getting ingested into the forecast models.
So I want to go back and talk about how are you able to determine, wind speed, pressure, and other factors with these storms, with these satellites?
Yeah, so one of the interesting things is you can actually use the satellites to look at the structure of the storm and gauge how strong that storm might be. So you're actually using infrared technology and almost image recognition to actually determine how strong the storm is. It gives us great information. We actually use it to send our hurricane hunters out towards the storm.
Do you think with technology so good nowadays, it's leading to the classification of more storms compared to what, 50 years ago, let's say?
That's a good question. I think one thing's for sure is that it's much harder to miss storms. Think about back to the early 1900s with the Galveston storm in Texas. Folks really weren't ready for that one. There wasn't a lot of notice. So I think we have better eyes. Certainly it's an exciting time to be able to watch things so closely. So yeah, I think it's much harder to miss things, and we're going to see that we're going to capture every little storm that's out there in the Atlantic.
Is it fair and accurate to say that the season we're seeing right now is similar to what we saw in 2005 when we made it through all the names?
That's a good question. We're outpacing as far as going through the names. We're outpacing 2005 right now. What's different about 2005 and this year is we don't have as many strong storms. The storms have been weaker and they've been shorter lived. This time through the K storm in 2005, we already had 5 or 6 hurricanes. So some similarities with 2005, but also some pretty big differences. I think the real question is, as we get into the peak of hurricane season, which is September 10th, what will that bring, and how many more storms will we see?
And I want to focus the question back to the satellites. And when you have a few storms brewing in the Atlantic, I know it must be busy, Noah, that is the meteorologist. What do y'all do? Do you focus on one? Are you just like all hands on deck, add more people to the team?
It really is an all hands on deck kind of moment. Really, different forecasters will focus on different storms. And as far as the hurricane hunters go, we'll be sending our aircraft out to the most imminent storms.
A lot of people saw the Saharan dust. We did here in central North Carolina. How did that impact the forecast, or just in general, the 2020 hurricane season?
That dust storm was really incredible. They originate from Africa and travel across the Atlantic basin. And they're the size of the lower 48 states as they come across. And we saw the largest one ever on record, which goes back about 20 years with our satellite record, the largest dust storm that we've seen. And it was pretty incredible. And it made its way all the way into the Gulf of Mexico. And as you know, it actually made it into the Southeast states. I was actually traveling through the Carolinas when that dust made its way up there. And there was that milky white haze and unmistakably Saharan dust all the way from Africa that had traveled about 7,000 miles. So that period really kind of stifled the tropical cyclones, because those dust storms really work against the hurricanes. And that's exactly what we saw.
What is the one thing you would like people to know?
I think I like people to appreciate that even if you don't live along the coast with these storms, to really be aware and pay attention as the forecasts are made. Even well inland, you can get severe weather. You can get inland flooding, which is a major cause cause of loss of life with landfalling storms is actually inland flooding. So even if you feel safe inland, keep an eye on things. We can get tornadoes along the outer bands of some of these storms.
And every storm has its own personality, that is for sure.
That's true.
Jason Dunyan with NOAA, thank you so much for your time, and we will certainly be in touch.
Thanks for having me.
And that was Laura Smith talking to Jason with NOAA. And you heard him mention the Galveston hurricane of 1900. Well, today is the anniversary of that hurricane making landfall. It was on September 8th, 1900, that the storm made landfall right around Galveston. Here is a weather map from that day. Those circles, while they look like a bullseye, those are isobars. And if you've seen us talk about hurricane forecasts, talking about the pressure of a system, well, isobars link up common pressure. And when they start to look like a bullseye that you'd use with a bow and arrow or archery, you know that it is an intense storm, because the more lines that you see and the closer that those lines are packed together, it's telling us a story that the pressure is pretty intense, either really, really high pressure or in this case, really, really low pressure. And that's what all tropical systems are, essentially, areas of low pressure. Well, this area of low pressure, one of the strongest we've ever seen, was getting ready to make landfall 120 years ago right now. Here's the path of the great Galveston hurricane back in 1900. Of course, back then, they didn't name storms, and they barely had any way to tell that they were coming, and I'll talk about that in a second. But it formed out in the tropical Atlantic, came right over the Caribbean, and even though it was pretty much over land through many of the islands through the Caribbean, including Cuba, it still emerged to the really warm waters of the Gulf of Mexico, strengthened to a Category 4 hurricane, and made landfall just south of this little area of water right here. That's Galveston Bay. They had storm surge that was some 15 feet tall. And here's what the devastating fact about this storm. When it made landfall, about 8 o'clock in the evening, there were people still out on the beach that morning. A Category 4 hurricane was about to make landfall, and that day, most people didn't even know it was coming. It resulted in some 8,000 to 10,000 fatalities, the deadliest hurricane in U.S. history. It left about a quarter of the Galveston residents homeless. It devastated homes, partially because when it made landfall, winds were 145 miles per hour. The storm surge was an estimated 15 feet tall. I'm about 6 feet tall. So imagine stacking 3 of me on top of each other almost, and that's how high the waves were coming in as this storm moved inland. And it devastated. It changed United States history. It changed our relationships with international countries in the Caribbean because of communications and how we can better communicate to alert us when these storms are coming. And this is what it did. Of course, back then, most structures were built solely out of wood. There weren't codes. And again, a devastating storm that made landfall on the Texas coast 120 years ago tonight. Thankfully today, with NOAA satellites, with great computer models, we know storms are coming 10 days ahead of time sometimes. They didn't even have 10 hours notice that this one was coming. So thankfully, we have great technology today, and we'll continue to use it to track the tropics right here every Tuesday night. And that's it for tonight's episode. Thank you so much for joining us on Tracking the Tropics. Don't forget, we're here every Tuesday night at 8 p.m. Eastern, and we appreciate you spending part of your night with us. Live in Raleigh, North Carolina, I'm Wes Hohenstein. Have a great night.